Let us start today's class. It is the last class of time independent perturbation theory for the degenerate case. Okay, this is another example for the time independent perturbation theory on degenerate cases. Okay, so like Stark effect, which we discussed in the last class, we have to discuss Zeeman effect also. Okay, so this is also one of the example of degenerate perturbation theory. Okay, Zeeman effect in hydrogen. So when hydrogen atom is placed in an external magnetic field, we know that the spectral lines will be splitted, and that will be that effect can be called as Zeeman effect. So Stark effect means it is the splitting of spectral lines when you place the atom in an electric field. So here it is the magnetic field and it should be weak magnetic field. Okay, so this is Zeeman effect and normal Zeeman effect. We take the perturbing Hamiltonian here as it is the value h, which is equal to minus mu dot b, where mu is the magnetic moment, b is the magnetic field. So both have direction, and we consider here mu as, you can see here, mu as the sum of magnetic moment of orbital magnetic moment of the electron and spin magnetic moment of the electron in a hydrogen atom. So we are not considering the magnetic moment of proton there because it's compared to electron, it's very small. Okay, so minus of mu is for first term, it is for the orbital magnetic moment, which is minus e by 2 me c into L vector. L is the angular momentum vector, plus minus e by me into c s vector. So s is the spin angular momentum vector, me is the mass of electron, and c is velocity of light. So this is the value of magnetic moment. You can see this in your spectroscopy experiment studies, or you can see it in angular momentum, quantum mechanics angular momentum class also you can see, or you can see this equation in your spectroscopy Zeeman effect section. You can see this magnetic moment value. So I am not deriving it here, we are just applying the term of magnetic moment, just substituting the magnetic moment here from the section of spectroscopy Zeeman effect. Okay, so why there is 2 in orbital angular momentum term, and why there is no 2 in spin angular momentum, you can understand that from there. Okay, so from the section which you studied in spectroscopy. So this is the equation you have to remember. Mu dot b, minus of mu dot b is written in equation 1. I have already said what already written here, where mu is magnetic moment of hydrogen atom and b is applied magnetic field. The first term in the bracket denotes the magnetic moment due to orbital motion of the electron, and second term denotes the magnetic moment due to intrinsic spin of the electron. Here we neglected the magnetic moment due to proton in hydrogen atom, and the applied magnetic field. Let us take the applied magnetic field B in the direction Z axis direction. So if you are taking B vector pointing towards Z direction, magnetic field direction, if it is in the Z direction, then H equation 1 we can write like this. We are taking the dot product, and it will be B is in the Z direction, so you have to write only the component of B, so component of L and S in the Z direction. So B dot L and B dot S will be B LZ and B SZ. Okay, so both are in the same direction, and cos 0 will be 1. So cos theta, cos 0, it becomes cos 0 and it will be 1. So the equation will be minus of minus, it will be plus EB by 2 MEC LZ plus 2 SZ. You have understood that? Okay. Question number 2. Now L plus SZ is JZ, isn't it? So we write 1 LZ plus 1 SZ. There you just substitute it as JZ. So EB by 2 MEC into JZ plus SZ, equation number 3. So this is the perturbing Hamiltonian here due to the magnetic field B. So here we are considering the time independent perturbation theory in degenerate case by applying the perturbing Hamiltonian as equation number 3. So when we calculate the energy by using magnetic field as few thousand of Gauss. So if magnetic field B is only a few thousand of Gauss and putting n is equal to 2, that is second energy level, the energy will be E h cut B by MEC. The energy of the level which has n is equal to 2, you can find it this you can see it in earlier energy determining this you have studied in BSc classes. It is E h cut B by MEC. It is n we have substituted as 2. That is why it becomes E h cut B by MEC. Okay. And this value is of the order of spin orbit energy. So we can consider H as a perturbing Hamiltonian of the hydrogen atom. So this is of the order of spin orbit energy. That is why we can write it as a small energy Hamiltonian. So it is a perturbing Hamiltonian. That's why we take it as a perturbing Hamiltonian. Now H commutes with the Jz and L square, we know that, and the first order correction to the energy will be expectation value of equation 3. So Hamiltonian, perturbing Hamiltonian's expectation will be the, we know already from the theory, degenerate perturbation theory, we know that it is the expectation value of perturbing Hamiltonian which gives the first order correction to the energy E1. So E1 we take it as expectation value of H. So we substituting the expectation value of H, take the constant out, EB by 2 MEC, we take it out, and we take the state as J, L plus or minus half and MJ. So this is the normal state. J can be L plus or minus half, L plus S, isn't it? So L plus or minus half, and MJ is the component of J in the direction of the magnetic field. So we take J is equal to L plus or minus half MJ, JZ plus SZ, JL plus or minus half MJ. So inner product. And now we have to take first term. So EB by 2 MEC is the constant, and the first term is JL plus or minus half MJ JZ. So Jz's eigenvalue, expectation value, you can replace it with its eigenvalue, and its eigenvalue is mj into h cut. We know that. But for SZ, the expectation value we need to find out. So for finding it out, SZ expectation value, I have written it there. It is, we are taking it in the state J L plus or minus half mj. Okay. So by substituting the value of state and its coefficient, you will get square root of h cut by 2 L plus or minus mj plus half by 2L plus 1 minus h cut by 2 L minus plus mj plus half by 2L plus 1 whole square. So this comes 2 times in the ket and in the bra. So we can take all constant out, and it will be that as it comes 2 times, so that is why we take square, and the ket bra is same, isn't it? So it is 1. JL plus or minus half mj, JL plus or minus half mj, inner product, it is 1. So the SZ expectation value will be h cut by 2 L plus or minus mj plus half divided by 2L plus 1 minus L minus plus mj plus half by 2L plus 1. So this is the value. After simplifying, you will get h cut by 2 mj by 12 plus 1. 2 will get cancelled and you will get plus or minus mj h by 12 plus 1, which is equation number 5. So SZ expectation we have got in equation 5. Now we have to substitute this 5 in 4. So JZ has expectation which is mj h cut and SZ has expectation which is mj h cut by 12 plus 1. Substituting that, you will get 4 is equal to E1, which is equal to E h cut by B by 2 MEC. H cut we have taken it outside. So mj plus or minus mj by 12 plus 1. Mj also we have taken out. So it is 1 plus or inside bracket it will be 1 plus or minus 12 plus 1. Okay. 1 plus or minus 1 by 12 plus 1. This is the value of first order correction, which is equation number 6. And we substitute 1 plus or minus 1 by 12 plus 1 as G, which is called Landage factor. So equation number 6 becomes E1 is equal to G into E h cut B mj by 2 MEC, where G is the Landage factor. This is the value of first order correction to the energy, equation number 7. Now we need to find the Landage factor for different states. So if you have S half state means half is the J there, total value of L plus half, that is what it's written there, S half. So S half state means L is equal to 0, isn't it? L is equal to 0. S means it is L 0. S state means L is 0. And here J is given as half. So L 0 means S also will be half. J is half. So L plus S is J. So S will be half. So L is 0, S is half. Then G from the formula it is 1 plus or minus 1 by 12 plus 1, isn't it? 1 plus or minus 1 by 12 plus 1. So after substituting that 1, here we take 1 plus because we have S in plus sign. So S is plus sign. S plus sign means we have to take 1 plus 1 by 12 plus 1. So 1 plus 1 by L is 0. So 12 plus 1 is 1. So it will be 2. So G factor for S half state is 2. And G factor for S minus half state. What is S minus half state? Let us see that. L is 0, S is minus half, and G will be then as S is minus, you have to take 1 minus 1 by 12 plus 1. So 1 minus 1 by 12 plus 1 is 1 itself, then it becomes 0. So G factor is 0 there. So S minus half state G is 0. For P half state, for P half state, that is L will be P state means L is 1 and S is half. S can be S here is minus half. Why it is minus half? Because the subscript is J there. J is L plus S. S, if it is minus half only, it becomes half there, isn't it? 1 minus half is half. So P half state means P subscript half, subscript is J there. So J is L plus S. L is 1 there. S should be minus half. Then only J becomes half. So G is equal to 1 minus 1 by 12 plus 1, which is 1 by 3. That is 2 by 3. So P half state G is 2 by 3. And P3 half state, that is L is equal to 1 and S is equal to half. So G is equal to 1 plus 1 by 3, which is 4 by 3. So these are the values of G values of different states. Now let us see the splitting of this 1s half, 2p half and 2p 3 by 2 states. Okay, so 1s half is splitted into 2 because G is 2 there, and you can see that all the values, the splitting, you can say it is how is it happening, the splitting, if you know J, the splitting happens from minus J to plus J. Mj will vary from minus J to plus J. So here 1s half has J which is half. So minus J is minus half, plus J is plus half. So it can move to only two, it can split into only two states, plus half and minus half. So next one is 2p half. There also J is half. So it can split into minus J to plus J. So minus half to plus half. Next one is 2p 3 by 2, where J is 3 by 2. So minus J to plus J means 3 by 2, half, minus half, minus 3 by 2. So 4 splitting can happen. That is how I have drawn the splitting. The splitting happens splitting does not depend on G factor, but it depends on the value of J. So if the value of J we know, then we know how much splitting it can happen, into which how many number of states it can split. So if you know the value of J, you can draw the splitting energy levels. So after drawing, I have shown the values of Mj for each state, and we have also shown the transition. The allowed transition happens with the selection rule, and the selection rule is delta Mj, which is plus or minus 1 and 0. So you can see here the allowed transition, which are delta Mj, which is either 1 or minus 1 or 0. So these are the allowed transition for the Zeeman effect. So it will be 3, 5, 6, 7, 8, 9, 10 transitions are there, shown there, from second state to first state. After applying the magnetic field, the splitting of energy levels happens for the first and second energy level is like this, and each transition corresponds to each spectral line in the Zeeman effect spectrum. Okay, Zeeman spectrum. So that's all for today's class. So we have completed the perturbation theory, time independent perturbation theory for degenerate case and non-degenerate case. We have studied examples for both the degenerate and non-degenerate case. Study it as essay with example. Okay, so example also can be asked separately as essay. So you study each one as essay. For first one, non-degenerate case, the theory and its example, harmonic oscillator, and then degenerate case, its theory and its example, Stark effect, hydrogen atom Stark effect, and now the last example is the same for non-degenerate case. The last example is Zeeman effect. So study it as essay.